Okay, so in this problem we have the function x times tangent of x, and we are going to sketch a graph of this function from negative pi over 2 to pi over 2 by finding these three things: the vertical and horizontal asymptotes, intervals of increase and decrease, and the relative extrema, then the intervals of concavity and the inflection points, and then the last thing after we have all that is we're going to sketch a graph. Okay, so I think the first thing that we should probably do is, since we're going to need them anyways to find all this, why don't we just find the first and second derivative right off the bat. So the first derivative, well, here we have to use the product rule. And what we're going to get is, so the derivative of the first is 1 times tangent of x plus x times the derivative of tangent, well, that's secant squared x. Okay, and then we can use this to find the second derivative. The derivative of tangent x is secant squared x. And then here we have to use the product rule again, so it's going to be 1 times secant squared x plus x times, now the derivative of secant squared, well, we have to use the chain rule, so we bring the 2 down, so secant squared x, so it's going to be x times 2 secant squared x, and then you take 1 away from the exponent, which is 1, so we don't write it, and then times the derivative of just secant. Well, the derivative of secant is secant x times tangent of x. Okay, and so we should simplify this a little bit. Notice that these two, we can add them together. And so what we get for the second derivative is going to be 2 secant squared x plus, this is going to be 2x, and then secant squared times secant, this is going to give us secant cubed x times tangent of x. Okay, so let's just leave it at that for now. So now we have our first derivative and our second derivative and the original function. Okay, so to find the vertical and horizontal asymptotes, well, first of all, we notice that horizontal asymptotes, it's not relevant, because to find the horizontal asymptotes, you take the limit as x goes to infinity and negative infinity. But here, the domain is already restricted, so it doesn't apply to find the horizontal asymptotes. If it wasn't restricted in the domain from minus pi over 2 to pi over 2, then we would take the limit to infinity and negative infinity and see where this goes. Okay, now for the vertical, remember the most common case is when the denominator of a function is equal to 0. Usually you have a vertical asymptote there. But this isn't a fraction. But we do know that the tangent function actually has a vertical asymptote at pi over 2 and at negative pi over 2. So what we should do is we should take the limit as x goes to negative pi over 2 of our function, and we should take the limit as x goes to pi over 2 of our function. Now the reason why we're doing that is because we know that just the tangent function by itself, without thinking about the x, goes to negative infinity as we approach negative pi over 2 from the right, and then goes to positive infinity as you approach pi over 2 from the left. let me just draw a little picture over here on the side. This is tangent, just to make sure that we're all clear on this. So this is negative pi over 2. This is pi over 2. And the tangent function looks something like, from negative pi over 2 to pi over 2, looks something like this. So it goes off to infinity. So what we should do is find the limit as x approaches these values and see where it's going. Okay. Also important to know is that we want to figure out if it does have a vertical asymptote, we need to know if it's going to negative infinity like it is here or positive infinity. So remember that what you do is you first just sort of plug it in and see what's going on. So negative pi over 2, if we plug that in for x, we get negative pi over 2 times tangent of negative pi over 2. Okay, now again, this isn't really like you're plugging it in, but you imagine trying to figure out what's going on here. So negative pi over 2, that's just a constant. So let's just look at this for a second. Tangent of negative pi over 2. Well, first of all, we have to note this isn't exactly 100% correct. Since our domain is from negative pi over 2 to pi over 2, what we're really doing is approaching negative pi over 2 from the right, because those are the values that are on our function. And we're going to approach pi over 2 from the left, because basically our domain is limited to this area right here. So we approach negative pi over 2 from the right and pi over 2 from the left. Okay, now notice that this guy, tangent, as x approaches negative pi over 2 from the right, tangent, meaning this whole term is going towards negative infinity. Okay, but then here you have a constant that's negative, so if you multiply, imagine this is negative, a really big number, by a negative constant, this guy is going to be going to positive infinity. Okay, so, well, that makes sense, right? Because this whole thing is going to negative infinity, but then you're multiplying that by a negative number, so that entire thing is going to be positive, but still going to infinity. Okay, so I think what I'm going to do is I'm going to make a set aside some space here to sketch my graph, so that as I get information, I can start putting it in. So here, this is negative pi over 2, and this is pi over 2. And I know that at negative pi over 2, from the right, since it's going to infinity, what I'm going to have is a vertical asymptote there. And I know that my function is going to be going to positive infinity there, because that's what I just found. Okay, now here, let's try to figure out what's going on here. Here we're approaching pi over 2, positive pi over 2 from the left. So let me plug it in and see what's going on. Tangent of pi over 2. Okay, so what's happening here is that, well, pi over 2 is just a constant. Tangent of pi over 2, though, as we approach pi over 2 from the left, tangent is going to positive infinity. Okay, so what we have is, imagine a positive big number times a positive constant. Well, this is going to be going to positive infinity as well. So what this is telling me is that here at pi over 2 I have another vertical asymptote, and it's going also to positive infinity. So see, notice it's already not the same as the tangent function, which goes to positive infinity and negative infinity. In between, this function that we have here is going to go to positive infinity on both negative pi over 2, and pi over 2. Okay, so that's good. Now, let's find the intervals of increase and decrease and the extrema. So remember, what you do is first you find the critical points. That's where the derivative is either equal to 0 or undefined. So why don't we turn secant into sines and cosines to make it a little bit easier for us. So why don't we do this? What we're going to have is sine of x. So tangent is sine x over cosine x. So this is the derivative right here. Plus x, secant is cosine, so this is going to be cosine squared x. And what I'm trying to figure out is when this guy is equal to 0. Well, first of all, cosine is equal to 0 at pi over 2, but it's not equal to, cosine isn't equal to 0 anywhere inside of this interval. Okay, so since cosine is never equal to 0, then what that means is that I can multiply both sides by cosine squared. And that's going to help me get rid of the denominators here. So what I'm going to have is sine x cosine x plus x is equal to 0. Okay, so here it would be useful to remember an identity. Notice that sine x cosine x, so this looks like an identity. Remember that 2 sine of x cosine x, this is equal to sine of 2x. Now this is one of the identities that you're supposed to know, but we can use this because then that means that if you divide both sides by 2, what you get is sine x cosine x equals 1/2 sine of 2x. So what we have is that 1/2 sine of 2x is equal to negative x. So this means that sine of 2x is equal to negative 2x. Okay, so, and then for this, well, the easiest thing to note, the only place where this is going to be equal is when x is equal to 0. Okay, now the reason why, if you, let's just do a tiny sketch down here. If you take a look at the sine function, remember that the sine function goes, okay, up and down and up and down. Okay, now, remember that so if you find the slope of the tangent line exactly at 0, the slope of the tangent line of sine right here at 0 is going to be exactly 1. And so what it is that, so negative 2x, well, this line goes down here like so. And so, well, here's negative pi over 2 and here's pi over 2, so the only place where those two intersect is right here, exactly at 0. Okay, so this is my critical point, 0, and that's the only one I have. So then once I have that, I can do my number line. So I'll put 0 here, and then I pick my my test points. And so my test points, they have to be between negative pi over 2 and pi over 2. So how about negative pi over 4 and positive pi over 4. Okay, so I'm going to plug those into the first derivative. And so my first derivative, well, it's kind of up to you. You can either plug it into the original one that we have up here, tangent plus x secant squared x, or you can plug it into this one that we turned into sines and cosines. So what do we do with? Let's do it with the first one. So we have tangent of negative pi over 4 plus negative pi over 4 secant squared of negative pi over 4. Okay, now here what we have is so tangent of negative pi over 4. So remember that you just care about the signs, and so if you can figure out what the signs are easily, it'll make your life a little bit easier. But I guess notice that secant squared, well, this is going to be, let's write this down. This guy is going to be positive. This guy is obviously negative. So negative times a positive is going to give me a negative. And tangent of negative pi over 4, this guy is going to be negative as well, because tangent in the fourth quadrant is negative. So a negative plus another negative, well, that's definitely going to be negative. So this tells me that my function is going to be decreasing from negative pi over 2 to 0. Okay, and then we can plug in pi over 4 into the same thing. Tangent of pi over 4 plus pi over 4 times secant squared of pi over 4. Okay, and again, I can just take a look at the signs here. Tangent in the first quadrant is positive. This guy is obviously positive, and secant squared is going to be positive no matter what. So what I have here is I'm adding a bunch of positive numbers. So this tells me that my function is going to be increasing. And so what that means is that we have a relative minimum at 0, at x equals 0, and if I plug in x equals 0 into the original function, well, that's 0 times tangent of 0. That's definitely going to be 0. So right here, at 0, 0, I'm going to have a relative minimum. And so it's going to be increasing in both directions. Okay, and well, really in this case, I mean, if you know that it's it has a vertical asymptote here, and you have the intervals of increase and decrease, you don't really need the intervals of concavity that much, but we should do them anyways, because sometimes, every once in a while, funny stuff happens. So let's find the intervals of concavity over here in this little space that we have left. Okay, so we have the second derivative is right here, this guy. And so this guy looks kind of complicated to solve, but you notice that you can factor out a 2 and a secant squared. So why don't we do that? This is 2 secant squared x, and then what I'm going to get is 1 plus x, and then the remaining secant x tangent x, I'm going to just write that as sines and cosines. So tangent is sine x, and then secant is 1 over cosine, and then with the tangent, the cosine from the tangent, I'm going to get cosine squared x. Okay, so we already know that cosine is 0 when x is pi over 2, but that's not in the domain, so we don't worry about it. But we set it equal to 0 and we try to solve this. First of all, well, secant squared is equal to 0. Remember, secant squared is 1 over cosine. So this guy is actually never equal to 0. So I don't really have to worry about him. So what I have to deal with is just this inside, set it equal to 0. So what I have is 1 plus x sine over cosine squared x is equal to 0. Okay, now if I multiply both sides by cosine squared x, so what we end up getting is x sine of x is equal to negative cosine squared x. Okay, now this isn't directly, I guess, it's not very easy to solve this. But since our domain is restricted from negative pi over 2 to pi over 2, there is one thing to note, is that this guy, well, you know, cosine squared without the negative sign is always going to be positive. So you put the negative there. So that means this guy is going to be always negative. Okay, now here, notice that sine, let me draw a picture of sine here. Sine, if you draw it from negative pi over 2 to pi over 2, sine looks like this. And so notice that from 0 to pi over 2, sine is positive and x is positive. So that means this side is always going to be positive from 0 to pi over 2. Now from 0 to negative pi over 2, x is always going to be negative. Sine is always going to be negative. So this guy is going to be always positive. Now note that this is from negative pi over 2 to pi over 2. So this doesn't have a solution. What that basically means is that there's no concavity change in the entire function. And so when I make my number line here, I'm going to go from pi over 2, from negative pi over 2 to pi over 2. And my test point can basically be anything I want, because there's no possible change in concavity, because this doesn't have a solution. So the easiest thing to do is to just plug in 0, and I can look at it right here. This is going to be so f double prime at 0. The easiest one to plug it into, I think, is this one. So what I get is secant squared at 0. Well, that's just going to be 1. So it's 2 times 1 plus 0. So this is positive 2. So this means that this guy is always going to be concave up, which makes complete sense with my information that I had so far. It has to be concave up, at least over here in the end, otherwise you couldn't have a vertical asymptote there. So this guy is going to look like this when we put it all together. It's actually symmetric, but I messed up my little drawing there. And so that's it.